Volcanic eruptions were common in Earth's past and are ongoing today. So now let's review the basics about the major types of volcanic structures that represent a wide range of volcanic eruptive styles. Shown here is a 1980s eruption at Pu'u'o'o, a vent in the eastern rift zone of the Kilauea volcano in Hawaii. Before we look at all the different types of volcanoes, let's review the main causes for the differences in volcanic eruptions and the volcanoes that result from them. The first factor is the amount of volatiles in the magma, and by volatiles I'm mostly referring to gases, and the most abundant gas by far is actually water vapor, H2O. So as magma rises, the pressure decreases and water violently flashes to steam, which propels the eruption. So a low amount of gas in a magma typically leads to an eruption that is fairly passive or not very explosive, like at this lava lake at the summit caldera of Kilauea. Whereas more gas in a magma can generate a much more explosive eruption, like what happened at Mount St. Helens in 1980. Let's visit Kilauea, seen here in the eastern part of the Big Island of Hawaii. This is the summit caldera complex of the Kilauea Shield volcano. You can see a number of pit craters, and the youngest one is Halima'uma'u, where an active lava lake formed between 2008 and 2018. Of course, Kilauea has been in a state of almost constant eruption since 1983. And the East Rift Zone has been the location of most of this activity. This is Mount St. Helens in 1980. Let's go there and see what it looks like today. Of course, Mount St. Helens is best known for its major eruption in 1980. This is the view to the north, the direction of the collapse and a lateral blast, which killed 57 people. A small lava dome represents the latest activity in a volcanic history that goes back almost 40,000 years. Periodic plumes of steam and ash were common between 2004 and 2008. Two other factors that control the type of eruption are magma composition and eruption temperature. Magma composition is typically measured in weight % silica, and eruption temperature in degrees C, both of which strongly influence the viscosity of a magma or lava. Remember, viscosity is simply the measure of a lava's ability to flow. Low viscosity lavas typically have lower weight % silica, like between 45 and 52%. We call this composition mafic. These lavas erupt at higher temperatures, like between 1000 degrees C and 1250 degrees C. These mafic lavas tend to flow easily, let gas escape easily, and erupt in a fairly passive, non-explosive fashion. High viscosity lavas have higher weight % silica, like greater than 63%, commonly up to about 75% or so. We call this composition felsic. These lavas erupt at lower temperatures, like between 600 and 800 degrees C. For these felsic lavas, flow is difficult, gas escape is difficult, thus allowing gas pressure to build up within the magma, and thus eruptions are more explosive. Here's Kilauea again, the summit caldera complex and the East Rift Zone. And as we move to the east, we can see other vents of the East Rift Zone, like Pu'u'o'o. Since 1983, numerous eruptions of highly fluid basaltic lavas have covered the landscape, some traveling all the way to the ocean. For instance, in 2018, the Lower Puna eruption produced numerous lava flows that covered about 35 square kilometers and created about 3.5 square kilometers of new land in the ocean. The 2008 eruption of Chaitén in Chile included growth of a large viscous rhyolitic lava dome within its older caldera. This eruption also produced pyroclastic flows and an eruption column that reached tens of thousands of meters in height. Here is a map of the world's major active volcanic centers. These are present on every tectonic plate and are typically related to a tectonic plate boundary or intraplate setting. The U.S. Geological Survey, or USGS, has a nice website with current volcanic activity in the United States. Click on the link and take a quick look. This is what I call the Volcano Review Table, a summary of the important characteristics of the main volcano types. I find this layout useful because it shows a lot of information on one page, but also that many volcano types have shared characteristics, like magma composition, viscosity, etc. And you can see those pretty clearly in this kind of format. There are 7 main volcano types listed across the top of this table, and they are primarily ordered based on their compositions. There are a few other important volcano types, like Mars and tuff cones, but they're not included in this table. In this lecture, we will review the important characteristics of these volcano types, and these are listed on the left-hand column. So let me describe these characteristics, starting with landforms, which describe the type of volcanic structure, whether it's broad volcanic plateaus or large steep-sided mountains, etc. Eruption products are what is being erupted, which may be mostly lava, lava plus tephra, or mostly tephra. Tephra is anything blown out of a volcano, like volcanic ash, blocks, bombs, that kind of stuff. Magma composition ranges from mafic to intermediate to felsic, typically from left to right, respectively. Magma viscosity is given as low, as with mafic magmas, moderate, or high, as with felsic magmas. Percent gas in the magma ranges from low to high. Brief descriptions of the eruptive styles are given, with the eruption type, if it has a specific name, given in parentheses. Explosivity ranges from low to ultra-high. Magma origin includes partial melting of the mantle, hydrous subduction zone melting, and crustal melting. Some volcano types are common in certain plate tectonic settings, but most occur in more than one. Examples of each volcano type are given, most around the world and sometimes from Arizona. Various volcanic hazards include lava flows, gas emissions, blasts, pyroclastic flows, ash fall, etc. Finally, a few comments are listed for each volcano type, and a copy of this table is available at the provided link. Let's start our discussion with flood basalts, a type of large igneous province. Flood basalts are eruptions of huge volumes of mostly mafic lava, or basalt. They can be on continents or in ocean basins. In red here are continental flood basalts, and they're present on every continent. And then in dark blue are oceanic plateaus, which are the oceanic equivalent of a continental flood basalt. So all of these are large igneous provinces. These eruptions involve huge volumes of magma, and thus lava. we're talking about hundreds of thousands to millions of cubic kilometers. Let's think about that for a second. A cubic kilometer is a cube, 1,000 meters on a side. So wherever you are, walk 1,000 meters in one direction, 3,300 feet or so. So it's about, what, 2/3 of a mile? And then take a right angle and go left another 1,000 meters, and then go up in the air another 1,000 meters. So that defines the edges of a cubic kilometer. Fill that with magma and you have 1 cubic kilometer of magma. And then erupt it out onto the surface. Well, that's pretty much what happened at Mount St. Helens in 1980. But think about this. Some of these continental flood basalt eruptions and even the oceanic plateaus, which can be even larger, involving millions of cubic kilometers. So imagine erupting millions of those cubes out onto this Earth's surface, not all at once, but over hundreds of thousands or a few million years. Flood basalts are exposed all around the world: North America, South America, Africa, Asia, and the oceanic regions as well. Shown here is an area of southern Greenland with rocks of the North Atlantic igneous province. And these basaltic flows were erupted roughly 60 million years ago as the North Atlantic Ocean started to form. This is an area of the Columbia River flood basalts. And if you've ever been to the Pacific Northwest, specifically eastern Washington and Oregon, you can see vast areas covered with lava, flow after flow after flow, and these broad plateaus are then cut by several major rivers, including the Columbia and the Snake. Flood basalts are formed by huge eruptions of highly fluid, low viscosity basaltic lava, forming flow after flow after flow, which we can see like this exposure in a hillside in the Columbia River area. Here are the extensive plateaus incised by a stream here. Within the walls of these stream canyons, you can see the volcanic stratigraphy. Older layers at the bottom followed by the eruption of the younger layers. We've never seen a flood basalt eruption in human history. We can only imagine what this would have looked like. This is an artist's rendering of what a vast outpouring of mafic basaltic lava would have looked like, a flood basalt eruption. That's fairly accurate. Notice that there's not a whole lot of boom going on. It's mostly eruption of highly fluid lava in a passive way, with local fire fountains and a lot of gas. We'll talk about that in a minute. These low viscosity basaltic lavas may be gas poor, but since the eruption volumes are so high and the lava is so fluid, the gas escapes rather easily into the atmosphere, or hydrosphere. So this is what a typical fluid basaltic lava looks like. Low viscosity, very runny, and that will solidify into the typical rock type basalt. And if there's any gas in that lava that is trapped, it'll form something that's more vesicular, has holes in it which represent those trapped gas bubbles. This is the rock type scoria. So you can have crystalline basalt, you can have vesicular basalt, you can have scoria. There's a whole range depending on how much gas is trapped in the lava. But typically a lot of that gas escapes. This is a typical eruption. All these fire fountains on a line here, this linear event, it's called a curtain of fire. And you can see the volcanic gases coming out, released directly, in this case, into the atmosphere. So what are those gases? Well, the number one gas is H2O, water vapor, but there's also SO2 and CO2. SO2 is basically sulfur dioxide. In large quantities, sulfur is emitted out of some of these types of volcanoes. When that sulfur combines with oxygen, you have sulfur dioxide, and then when you combine that with water, you have a dilute sulfuric acid. With CO2, when that's emitted, that can combine with water vapor to form a weak carbonic acid. So these are both prominent volcanic gases as well. In terms of sulfur, that can be present in very large amounts in some of these magmas. Different magmas have different flavors, and some can be more sulfur-rich. Typical eruptions that kill away these days aren't so powerful, so the gases basically stay low in the weather layer, in what we call the troposphere. The first few kilometers of the atmosphere where then rain and wind can scrub those gases out of the atmosphere. This haze that's produced, this volcanic smog, if you will, the locals in Hawaii call it VOG. And sometimes it travels from the Big Island to the west, taken by the trade winds over to Oahu. So they don't have bad smog days, they have bad VOG days. But that's not a global kind of problem. The problem comes when the eruption is powerful enough to form eruption columns which thrust the gas higher through the troposphere into the stratosphere, where then the gases can be distributed around the world. And this would basically form an envelope of high-level haze, which tends to block sunlight and thus cool the planet. Now, CO2 erupted in large quantities would tend to do the opposite, trap heat and maybe warm the planet. But SO2 is definitely a player when we have large volcanic eruptions. Flood basalt eruptions likely occurred along multiple fissures, and while the lava discharge rate is relatively high, the explosivity is probably rather low. So while flood basalt eruptions have not occurred in human history, and that's a good thing, much smaller but similar eruptions occur in places like Iceland and Hawaii. This is a linear vent in Iceland. Here is a curtain of fire going on right now. You can see again the gases being emitted. Flood basalts are related to the massive decompression melting that occurs near the top of a mantle plume. Mantle plumes are generally formed with a head and a tail, and the head forms because the plume is at shallow levels and the pressure is less, so the hot rock expands, and if the pressure is low enough, you'll get decompression melting on a fairly large scale. And so as that plume head expands, the overlying lithosphere will be arched up. And as it does that, it gets fractured, and those fractures can be pathways for magma to travel through and the lava erupt on the surface in large quantities. This can happen underneath continental lithosphere, forming a continental flood basalt, or an oceanic lithosphere, forming an oceanic plateau. An example of a continental flood basalt in the United States is the Columbia River flood basalt. And here it is in the wild, showing the multiple basaltic flows in these cliffs. The geologic map on the right there shows the distribution of the Columbia River flood basalts in that puke apple green color. The Cascade volcanic range is the north to south map unit with the red triangles. Those are the individual volcanoes. Those aren't related to the Columbia River flood basalt. So you can see much of eastern Washington and northern Oregon are covered by the Columbia River flood basalts. And that represents roughly 175,000 cubic kilometers of lava erupted only 15 or 20 million years ago. There's a larger eruption over in India called the Deccan Traps, and this occurred roughly 66 million years ago. And this is what it looks like now. Again, you can see the layered nature of these lava plateaus. This had an eruption volume of a little over 1 million cubic kilometers. So maybe as high as 1.2 million cubic kilometers were erupted out right at the end of the Mesozoic era. The Deccan Traps in west-central India represent the eruption of about 1.2 million cubic kilometers of basaltic volcanics during the latest Cretaceous and earliest Tertiary periods, between 67.4 and 64.6 million years ago. About 80% of the total Deccan Traps erupted volume occurred just before the Cretaceous-Tertiary boundary, where the KT mass extinction occurred. There's an even larger eruption farther north in Asia, in Siberia, called the Siberian Traps, and that has an estimated volume of 2 to 4 million cubic kilometers. It's hard to tell exactly because much of it is buried at depth, and so it has to be estimated. But that's a very large continental flood basalt, and that occurred about 250 million years ago at the end of the Paleozoic era. Large oceanic plateaus include the Ontong Java Plateau in the southwestern Pacific, and this is quite possibly the largest outpouring of volcanic material in Earth's history. This event covered 1% of the Earth's surface, with millions of cubic kilometers of lava, forming a giant oceanic plateau. Of course, there are other oceanic plateaus like the Kerguelen Plateau in the southern Indian Ocean, but nothing as large as the OJP. Although flood basalt eruptions have not occurred in recorded human history, they have likely played a role in the evolution of life on Earth, at least in the last 500 million years or so. This diagram shows the ages of various flood basalt eruptions on the horizontal axis, with the ages of extinction events on the vertical. And you can see that there's a nice correlation between the two. Anytime you can get this many data points to form up along a straight line, you know that there's a pretty decent correlation. So, starting about 250 million years ago, the Siberian traps erupted in Asia, and remember that was 2 to 4 million cubic kilometers of flood basalt. That eruption occurred at the same time as the greatest mass extinction of all time, at the end of the Permian period, at the end of the Paleozoic era. It's estimated that 90% of life on Earth went extinct during this event. And so the Siberian traps were the most likely factor in this mass extinction. We can see other flood basalt eruptions. Not all of them correlate with major mass extinctions. Sometimes there are lesser extinction events. But at the end of the Mesozoic era, there is the Deccan traps. This helped contribute to the demise of not only the dinosaurs, but pterosaurs, marine reptiles, and other creatures. Those are two major volcanic eruptions which disrupted not only the lithosphere, but the hydrosphere, atmosphere, and even the biosphere. What happens when these events occur underneath the ocean? Well, they form oceanic plateaus, like the Ontong Java Plateau. These can also affect Earth's various systems and lead to what are called ocean anoxic events. So the eruption of those lavas still produces gas, which goes not into the atmosphere directly, but into the water, and it changes the chemistry of the water and causes it to be more oxygen poor or anoxic. So those are notable, significant events as well. While the amounts of lava produced during these events were not a major factor in the mass extinctions themselves, it's the tremendous amounts of volcanic gas, carbon dioxide and sulfur dioxide specifically, that were released and added to both the atmosphere and hydrosphere that would have significantly affected the biosphere. Shield volcanoes are broad mountains with low-angled slopes. These mountains span a range of sizes and can be quite large, reaching heights of over 9,000 meters. The central vent may include a small caldera complex that may fill with lava, forming a lava lake. Small cinder cones may also form on the flanks of the shield volcano. Basaltic lava is the dominant material erupted from a shield volcano, with small amounts of tephra usually as well. Remember, tephra is a pyroclastic material like blocks and bombs, lapilli, and volcanic ash. The basaltic lava itself is highly liquid, low viscosity, thus it cannot build up steep slopes. So it flows out and forms plateaus, or eventually, since it's coming out of one basic area, it starts to build up a low, broad mound, which on its side was first described by Pliny the Elder in ancient Rome as a Roman warrior's shield on its side, a shield volcano. These lavas, in their fluid nature, prevent them from building up large, steep-sided cones. So that's why you get gently sloping flanks on a shield volcano. Eruptions themselves are typically passive, with fire fountains and curtains of fire erupting from both the central vent and from fissures on the flanks. You can see the fire fountain here, and you can actually stand quite close to these because they are relatively passive eruptions, although they are quite hot. And you would need your asbestos-lined suit, like Maurice and Katja Kraft wore. They actually wanted to line a canoe with asbestos and basically float down one of these lava flows. Kinda nuts, but it does demonstrate the fact that you can get fairly close to these eruptions if you're equipped with the right gear. The Big Island of Hawaii is composed of 5 distinct shield volcanoes. Mauna Loa is the largest of these and towers about 13,000 feet above sea level. However, it measures about 30,000 feet from its base on the seafloor. Indeed, it can be considered the largest single mountain on Earth. Fernandina, it has a slightly different shape, like an inverted bowl, but it is a shield volcano in the Galapagos Islands of the eastern Pacific Ocean. Mauna Loa is an active shield volcano that began erupting anywhere from 1 million years ago to maybe 600,000 years ago. The latest eruptions were in 1984. Like Mauna Loa, Fernandina is another hotspot-related shield volcano. Most recent eruptive activity was in 2020. Arizona is host to several examples of shield volcanoes, one being Joe's Hill along I-17 in central Arizona, just north of Phoenix. This small shield volcano was once active as late as 10.6 million years ago, when it might have looked like this. Another small shield volcano is Arlington Mesa, located just west of Phoenix. This small shield volcano was active 1.3 million years ago, and this is what it could have looked like. Here's Joe's Hill, a shield volcano vent that produced lavas that filled the lowlands between the Bradshaw and New River Mountains in central Arizona. Today, the basaltic lavas cap broad mesas that are incised by streams like the Agua Fria River. Look for Joe's Hill just east of I-17 near Sunset Point. Cinder cones, sometimes called scoria cones, are relatively small conical volcanoes with moderate slopes of 20 to 30 degrees or so, and tend to be several hundred meters high. They are formed mostly of pyroclastic debris, or tephra, blown out of a central vent. The slopes are layered mafic lapilli, or basaltic cinders, that are commonly oxidized to a reddish color. Cinder cone magma typically has a moderate amount of gas, which results in a moderately explosive eruption and eruption column. Cinder cone eruption may include a small eruption column that may send tephra thousands of feet into the air, some of which may be scattered downwind, but most of it falls back down around the vent, forming a cone. Small basaltic lava flows may be associated with cinder cone eruptions. This is the nighttime eruption of a rather famous cinder cone in Mexico called Paricutin. Here you can see the fire fountain occurring right at the vent, and much of the material falling down around the slopes incandescent, and those are blocks and bombs. Cerro Negro is an active cinder cone in Nicaragua. I wonder why they called it Cerro Negro. Anyway, you can see the small eruption column with the tephra falling out of the eruption column right back down onto the cone. This is Paricutin in Mexico, and this cinder cone first erupted in the 1940s. Again, rather small eruption column here with tephra falling out either around the cone or in a nearby area. Paricutin, located in the Michoacan, Guanajuato volcanic field, about 200 miles west of Mexico City, is a very young cinder cone. You can see it here with the cone and related lava flows. It first erupted in 1943 and continued for 9 years, and by 1952, the cone had grown to about 1,400 feet in height. Paricutin's story is also told in the children's book Hill of Fire. Arizona is home to several fairly young mafic volcanic fields, like less than a few million years old. One is the San Francisco volcanic field, which includes several hundred cinder cone volcanoes, one of which is SP Mountain. And this cinder cone and its 4.5-mile long lava flow erupted about 71,000 years ago. This is what SP Mountain might have looked like if you were around back then. Sunset Crater is the youngest cinder cone in the San Francisco volcanic field, and it's thought to have erupted first around 1200 AD. So if you were around 800 years ago, this is what you might have seen at Sunset Crater. SP Mountain is one of my favorite places. It's a cinder cone that you can hike up and hike around and explore, and then scramble down the slopes when you're done. The SP Mountain cinder cone and its 4.5-mile long lava flow erupted about 71,000 years ago, although this potassium argon date may not be reliable. You can see two places where the lava levee along the edges of the flow have been breached. The history here had the flow coming first, followed by the eruption of the cone. So you can see the cone sitting right on top of the flow with no disruption in the cone and no flow coming down the sides of the cone there. So the cone wall is not disrupted. See, this cone has a sharp-edged rim of welded spatter and agglutinate, which gives SP its nice distinctive profile. According to lore, it was named by local ranchers for its resemblance to a chamber pot, but the USGS shortened it to SP. Sunset Crater National Monument is home to Sunset Crater and its two lava flows. This crater, unlike SP Mountain, you can't hike up. It's off limits to hiking. Its oxidized cinders give it its name, and it's a really cool place to visit. So let's check it out. The 1,100-foot-high cinder cone and its two lava flows last erupted about 900 years ago and is the youngest known volcanic feature in Arizona. Beginning in the 1080s AD, Strombolian eruptions form the initial cone and the Bonita flow to the west. Followed by more cone building and eruption of the Kanaa flow to the east. The eruptions produced ash that covered more than 2,100 square kilometers and forced the local Sinhala people to relocate, but they eventually returned and took advantage of the fertile soil. Stratovolcanoes, or composite volcanoes, are a classic volcano type that we are all familiar with. These large, steep-sided mountains can reach heights of up to 3,000 meters and are often capped with snow. Stratovolcano eruptions involve a mix of both lava and tephra, which are layered together to form steep-sided slopes. The moderately viscous intermediate magma is strong enough to hold a higher slope than the more mafic volcanoes. This diagram here shows the fundamentally interlayered nature of a stratovolcano, with the intermediate andesitic lavas interlayered with pyroclastic material like volcanic ash. And while the intermediate lavas are relatively strong, moderately viscous so they can hold a decent slope, the pyroclastic layers are relatively weak, especially when they are hydrated, flushed with water, like you can get from snowmelt or from groundwater. This inherent weakness lends itself to collapse of parts of the volcanic cone, which can lead to further eruptions. The combination of more viscous magma and higher gas content results in powerful eruptions, which produce large eruption columns, dangerous pyroclastic flows, and widespread ashfall. These volcano types form from hydrous melting in a subduction zone tectonic setting. The subduction zones forming the so-called ring of fire around the Pacific Ocean include many such active stratovolcanoes. This is an eruption, and there's two parts to it. There's the eruption column, which is the vertical convection of material out of the volcano, and then there's the pyroclastic flow coming down the flanks of the volcano. The pyroclastic flow can be from collapse of the eruption column, or it can be part of a more lateral blast. The eruption columns in stratovolcano eruptions are often powerful enough to reach altitudes extending into the stratosphere, thus distributing fine-grained volcanic ash around the world. This can result in a small but significant decrease in global temperatures, as high-altitude ash blocks incoming solar radiation. You can see the enormous eruption column expanding and mushrooming as it gets higher and higher. This is a volcano in the Aleutian Islands of Alaska. You can see the light and dark nature of the eruption column, and then you can see a very high top to the eruption column there. This is a eruption going on in the Kamchatka Peninsula, and you can see that it is being spread laterally quite some distance from the volcano. And so an eruption typically involves first the magma, release of pressure, and the expansion of gas. This is what's called the vesiculation region of the upper magma chamber and into the volcanic conduit. And then there's the active gas thrust region, which is typically within the throat of the volcano and then out the top. And then the eruption column itself has two parts. It's the gas thrust region, where it's being actively driven by the expanding gas, and then the convective thrust region, which is more heat related. And then it tops out and forms an umbrella region. And that's kind of what we're seeing here in Pinatubo and here in the Aleutians. That's usually high enough to be in the stratosphere, and that's where the material gets carried downwind for quite some way, possibly around the world. Whereas material that doesn't make it that high typically falls out in the lower levels of the atmosphere. There are many important and well-known stratovolcanoes present around the world. Some of these include Mount St. Helens in Washington. This picture is from previous to its catastrophic eruption in 1980. This is Mount Fuji, or Fujiyama, in Japan. Mount Mayon in the Philippines is a classic stratovolcano that is constantly erupting. And Popocatépetl, or El Popo, just to the southeast of Mexico City. At 17,802 feet, El Popo is the second highest peak in Mexico. Its twin to the north is Iztaccíhuatl. El Popo is located about 70 kilometers southeast of Mexico City. This stratovolcano has been active since the Pleistocene, about 730,000 years ago, with the last major Plinian eruption occurring around 800 AD. El Popo is currently active, with numerous recent small eruptions of rock, ash, and steam. The most famous and well-preserved stratovolcano in Arizona is San Francisco Mountain, which includes the San Francisco Peaks, and this is located north of Flagstaff. This volcano was active from about 2 million years ago until about 400,000 years ago, and last erupted about 420,000 years ago, when it might have looked like this. So that's the kind of thing a volcanologist like Dick Holm has figured out. So this is the view from the west side, and these are the peaks. You're looking at a couple of them. This is Agassiz Peak, and this is Mount Humphreys, the highest point in Arizona. And so this is the view from the east side near Sunset Crater. And again, you can see some of the peaks with Agassiz in the back and then Humphreys over here in the back on the right. When I was first driving into Flagstaff as a graduate student, I saw these peaks and I thought each one of them might be a volcano because they have that kind of shape. But indeed, this mountain was one volcano. If you extend the slopes up from either side, they meet at a point in the air at about 15 or 16,000 feet, a few thousand feet higher than the peaks are today. That's where the summit of the ancient volcano was. And so collapse of the volcano and some of the final eruptions took out a lot of material, but why the peaks look like they do today is because they've been glaciated. It's one of two areas in Arizona, the other being in the White Mountains. So here's a look at San Francisco Mountain. And the San Francisco Peaks. Again, this mountain was formed over the last 2 million years or so, and two major stratocones formed here. With the last eruptions occurring about 400,000 years ago. And this cone was destroyed by a large collapse on its northeast side. Here are the San Francisco Peaks, interior valley, and inner basin. And Humphreys Peak, the highest point in Arizona. Lava domes are small, steep-sided volcanoes that are typically associated with stratovolcanoes and calderas. Lava dome magma originates from melting of continental crust, and upon eruption, highly viscous felsic lava combined with moderate to high amounts of gas produce small but powerful eruptions and dangerous pyroclastic flows. This shows the typical structure of a lava dome. Its highly viscous nature prevents it from flowing, so it basically just piles up around the vent. When material is added from the inside and pushes the older material out, that's something we call an endogenous dome. Endogenous, it means it grows from within. Sometimes the lava will squirt out the top and flow down the sides. You'll get short flows down the side, and that's called an exogenous dome. It means it's flowing on the outside without. Those are two different types of dome structures. They essentially form the same kind of shape. Small lava dome like this. Mount St. Helens lava dome here releasing some steam. Mount Unzen was a larger lava dome complex here generating a dangerous pyroclastic flow. Just ask this person. Pyroclastic flows are one of the most dangerous volcanic hazards, and so if you're on the mountain when this happens, there's not a whole lot you can do, as they travel very fast and they are hot and relentless. And these are the types of rocks you typically see in a lava dome, whether it's rhyolite, or pumice, vesicular felsic lava, and then there's volcanic glass. Volcanic glass is darker like that. Again, not because it's got iron and magnesium and calcium in it. No, it's because of the amount of inclusions in it and the amount of gas bubbles in it. And so if there's more bubbles, they reflect light better. It's kind of like dark beer. When you pour dark beer, the beer itself is dark, but the foam is very light. And the foam is light because bubbles are scattering the light. And so when you see black obsidian like this, it's typically got the same composition as this rhyolite or even this pumice. It's just more poor in gas bubbles. Examples of lava dome volcanoes include the lava dome inside Mount St. Helens, the lava dome complex at Mount Unzen in Japan, Mont Pelée in Martinique, lava dome inside the Nova Rupta volcano in Alaska, and even the small Salton Buttes in California. The Mount St. Helens lava dome has grown since the eruption in 1980, and it periodically releases gas, sometimes in pulses, sometimes just like this, and it's fairly well documented. There are a number of webcams that stream footage from the crater, so it's pretty neat to check it out every once in a while. Mount Unzen is the dangerous volcano in Japan that erupted, and there was a meeting there with a bunch of geologists, and some of them warned that the volcano was in imminent danger of eruption, and some of them, including Maurice and Katja Kraft, perished along with a number of other people. Mont Pelée in Martinique produced quite possibly the deadliest volcanic eruption of the 20th century. In 1902, it erupted and the city of Saint-Pierre was wiped out by pyroclastic flows, and 29,000 or 30,000 people perished in that eruption. Nova Rupta is a small classic lava dome here, like a rubble pile, but that is in a larger caldera, and it's in an area called the Valley of 10,000 Smokes. Smokes being volcanic gases, fumaroles we call them. Okay, and then the Salton Buttes are little lava domes on the shores of the Salton Sea in southeastern California, and they're testament to the fact that there is a magma at depth. The geothermal gradient is high enough there to produce magma, and you get these small volcanic vents. Not a huge volcanic field, but their presence is noted nonetheless. Mont Pelée, on the Caribbean island of Martinique, is an infamous volcano. It's been active for several 100,000 years, but is most notable for its 1902 eruption, which produced pyroclastic flows that destroyed the nearby city of Saint-Pierre, killing 29,000 to 30,000 people in the course of a few minutes. Activity more or less ended in the early 1930s, but Mont Pelée is still considered active. The San Francisco volcanic field of northern Arizona includes many different types of volcanoes. One of them is Eldon Mountain, which is present just to the south of San Francisco Mountain in Flagstaff, and it's an exogenous dome. Lavas were coming out from the summit and pouring down the sides. And this last erupted about 550,000 years ago, when Eldon Mountain might have looked like this. And then there's also Sugarloaf Mountain, which is present on the eastern side of San Francisco Mountain, and it last erupted 220,000 years ago. And it might have looked like this. It erupted after San Francisco Mountain had collapsed. We know that from the dating of the different units, but we also see that this lava dome is present on top of those eruption units from San Francisco Mountain. There's several other lava domes around the mountain. On the northwest side, there's the White Horse Hills, and there are other ones around. Eldon Mountain is what's called an exogenous dome, meaning that it grew as viscous dacite lavas flowed from a summit vent down its outer slopes. You can plainly see these viscous lava flow lobes all along the perimeter of the mountain. several flows actually solidified while still on the slopes. Sugarloaf Mountain on San Francisco Mountain is what's called an endogenous dome, meaning that it grew as lava is pushed out from within the dome. Here's seen from the Lockett Meadow side. This dome erupted after the collapse of San Francisco Mountain. It is an age of about 220,000 years. It erupted through glacial sediment, and the initial part of the eruption produced a significant amount of volcanic ash, which you can see here. And this occurred in a violent hydromagmatic eruption, as the magma hit water and you had a giant steam blast with the magma erupting at the same time. Then the lava dome was emplaced over top. Calderas are the final volcano type we'll talk about in our review today. These are typically large circular depressions that may be tens of kilometers wide. Caldera magmas originate by melting of the continental crust. Eruptions typically emanate from a series of circular fissures, and as the level of the magma in the chamber decreases, the roof rock is destabilized and eventually collapses into the magma chamber, forming a circular depression or caldera. This may then reinflate as magma reinflates the magma chamber, and it might push the floor of the caldera up. And this kind of pistoning effect is fairly common. And so you can get what's called a resurgent caldera and another eruption. And so you can get a number of different eruptions in this cycle. Caldera eruptions typically involve massive amounts of tephra, volcanic ash, and relatively minor amounts of felsic lava. The highly viscous felsic lava, combined with the moderate to high amounts of gas and high eruption rates, produce powerful eruptions, towering eruption columns, dangerous pyroclastic flows, and vast ashfall blankets. Some well-known calderas from around the world include the Yellowstone caldera in Wyoming. And in this picture, you can't really see the actual landform that is the circular depression. It's fairly large, and it's covered with vegetation. Crater Lake in Oregon, you can see the actual topographic feature. There's the circular landform, and it occupies the position where the Mount Mazama stratovolcano used to sit. And several thousand years ago, it underwent a catastrophic eruption, and this caldera formed. And soon thereafter, a small volcano was produced inside Crater Lake, and this is called Wizard Island. And you can actually hike down, take a boat across, and hike around Wizard Island. This is the Valles caldera in New Mexico, just to the northwest of Albuquerque and to the west of Santa Fe. And then Krakatoa in Indonesia is actually a large caldera here, and Anak Krakatoa occupies a location within the caldera. Now to Crater Lake, Oregon, in the Cascade Range. Formerly the site of the Mount Mazama stratovolcano. Which experienced a catastrophic ultraplinian eruption and collapse about 7,700 years ago. The lake is almost 2,000 feet deep and is the deepest in the United States. You can also see the cinder cone Wizard Island that erupted within the caldera. The Valles caldera in northwest New Mexico is the younger of two calderas and formed about 1.25 million years ago. After its initial eruption, resurgent domes began forming until about 68,000 years ago. A seismic low-velocity zone beneath the caldera suggests a magma chamber at 5 to 15 kilometers depth. Several areas in southern Arizona are home to calderas or caldera-related volcanics, and these include the Superstition Mountains in central Arizona, just east of Phoenix, the Cofa Mountains in southwestern Arizona, near Yuma, and the Galliero Mountains and Chiricahua Mountains in southeastern Arizona. All of these mountains formed during caldera-related eruptions between 20 and 35 million years ago. These locations are within what's called the Basin and Range province, which between, say, 25 million years ago and about 10 million years ago experienced a significant crustal extension. So most of these volcanoes occurred at or before this extension. So that's why you don't see the original caldera structure anymore, because it's been destroyed by faulting and erosion. In fact, the superstitions, these units right here, were deposited within the caldera, and the walls of the caldera have been removed by erosion and faulting. And so what you're seeing was actually inside the caldera. So when you look at these areas, you don't necessarily see Crater Lake. Okay, so the superstitions were once thought to have formed in 3 different caldera locations over a time period of about 10 million years. Recent mapping by the Arizona Geological Survey has documented one large caldera structure that produced most of the volcanics in a 3 million year period between 21 million and about 18 million years ago. The Cofa Mountains in southwestern Arizona, jagged, beautiful country, similar age volcanics, and the Galliero Mountains in southeastern Arizona are home to Aravaipa Canyon, which is a beautiful hiking area. The Chiricahua Mountains erupted anywhere between 27 million and about 35 million years ago. One of the later eruptions, the Turkey Creek caldera, was a massive eruption in this area. In the Chiricahua Mountains of southeastern Arizona, the Turkey Creek caldera formed about 27 million years ago and involved the eruptions of huge amounts of rhyolitic tuff. Finally, just as with flood basalt eruptions, caldera eruptions can have a pronounced effect on global climate. While the amount of lava produced in a caldera eruption is rather minimal, great amounts of volcanic ash are erupted into the atmosphere, which can block significant amounts of sunlight and act to cool the planet. This diagram shows the volumes of several major caldera eruptions in the last 30 million years. And you can see some of these eruptions produced several thousand cubic kilometers of tephra. That's a lot of ash that went into the atmosphere. For reference, Mount St. Helens, 1980, produced about 1 cubic kilometer of tephra. So you might be thinking, Dr. Bob, I remember what you said about flood basalts, and they typically produced hundreds of thousands to millions of cubic kilometers of eruptive products. And that's true. But flood basalts are fundamentally different than calderas. They're producing almost all lavas and very little tephra. So the major climate change factor in a flood basalt eruption are the gases, the sulfur dioxide and carbon dioxide that are exhaled out of the magma and into the atmosphere or hydrosphere. Whereas a caldera eruption, you're getting tephra blown directly into the atmosphere, along with volcanic gases. So when you think again about one of those cubic kilometers, 1,000 meters on a side, okay, instead of filling it up with lava, fill it up with volcanic ash. And then say the Toba eruption 73,000 years ago, there's 2,800 of those cubes thrown into the atmosphere. High up into the stratosphere and then around the world, that's enough ash to block a significant amount of sunlight and actually make a dent in the global climate. And you have to wonder, it's like, how much ash is necessary to actually start blocking sunlight? Even with stratovolcano eruptions like Krakatoa and even Mount Pinatubo, we see a few degrees of change in global temperatures for several years afterward. So these major caldera events likely cause significant changes, cooling effects to the global climate. And so the biosphere was likely directly affected by each one of these major eruptions. We're just lucky because there's not been a recorded super caldera eruption, or super volcano eruption as they're sometimes called. There has not been one of these types of eruptions in recorded human history. So that's a good thing. Well, that's all for now. Till next time.